The purpose of this lab is to compare the similar motion of three objects that were dropped from rest and fell straight down. I want to demonstrate that all objects, regardless of their mass, fall at the same rate. A common misconception is that objects with a greater force due to gravity fall faster than those with less gravitational force. This is absolutely incorrect. It does not matter how big the force due to gravity is. All objects above Earth will fall at the same rate, 9.8 meters per second, and therefore they'll have the same speed when they hit the ground if they travel through the same distance of Earth's gravitational field. To show this, I dropped a piano, a bowling ball, and a solo cup from the same distance. I constructed computational models of each of their motions and finally extracted each of their final velocities when they hit the ground. For the piano and the bowling ball, I ignored the effects of air resistance. This means that the only force is the force of gravity acting downwards on the cup. For the dropping of the cup, I wanted to touch on adding the effect of air resistance and discuss what effects air resistance has on the object's motion. My results for the cup showed that both of my models overpredicted the position during almost the entire interval. My models of gravity and drag were almost identical until time equaled about 0.3 seconds. Then the plot of gravity and drag is greater than that of gravity alone. Here's what happens when I input each mass individually and run the tracker program. Each two lines represents one running of the program, each for a different object. The bowling ball comes first, then the piano, and then finally the cup. Notice that all the objects have the same final velocity. If they fell through the same space under the same force, then they must have been accelerating at the same rate the whole way down. Notice that they have significantly different masses, but their final velocities are precisely the same. This is not to say that they exhibit the same force when they hit the ground, nor is it saying that they all have the same gravitational force. So I'm proving that the mass of the object has no effect on the object's acceleration. Here's a photo of my system. For this trial of the cup, I dropped it from eye level. I dropped it upside down so the air resistance would be more noticeable in the model. I oriented my system in the following way. The bottom of the cup is the origin, towards the floor is then the negative y direction. The y initial velocity of the cup is 0 in both the x, y, and z axes. I began my tracker analysis as soon as my hands were off the cup. This way, all the analysis was of a free-falling object. During my tracker analysis, my video became blurred as the object dropped, so I chose the middle of the blur as my point mass for my tracker analysis. The time interval for the tracker analysis was t equals 0 to 0.567 seconds. Finally, I prepared my calibration stick to be the height of the cup, a known value of 0.121 meters. To construct the first model of gravity alone, the net force for Newton's second law was only the effect of gravity. This was simple. F net equals the mass of the ball in meters times negative 9.8, the quantity of the acceleration of gravity in meters per second. This is negative because I chose the y-axis upwards to be positive. To formulate the next model of gravity and drag, I included in my net force the force of gravity from the previous example, but also added a force due to drag. Lab instructions indicated to model the effect of drag by a force whose direction is opposite to the direction of motion, and whose magnitude is proportional to the square of the object's speed. To get this relation into code, I use the mag function, which takes the magnitude of whatever you put in parentheses, in this case, a vector. In this model, I also added the drag force with a yellow arrow. With both of these net forces, I formulated the Python module to repeat Newton's second law from 0 to 0.567 seconds. Since there is no way to calculate the b value, the proportionality constant, I plugged in values around 0.017 until my final position from the Python module equaled my final position in tracker. I had to do these steps for both modules. As you can see, the experiment position is nicely parabolic, something to expect from a free-falling object. This is because the force of gravity interacting with the cup is accelerating the cup downwards at a rate of 9.8 meters per second. Therefore, the slope of the experiment position versus time is getting more and more negative, and therefore is parabolic. As you can see, there's some discrepancies between my two models and my experiment position. I believe that the difference between both model plot and the experiment plot is due to my human error in the tracker point mass plotting. Both models, in comparison with the experiment, show that the cup is lower than it should be. defining what it should be as the model of the effects of gravity and drag, what happens in real life. If I had chosen a point mass in each frame slightly higher than I did, then the tracker's outputted y values would be slightly greater than they are now. This would result in less discrepancy between the experiment and model plots. Let's briefly compare the two plots. The model of gravity's effects has a final position greater than the effects of gravity and drag. This is because, with a drag force in the opposite direction of motion, the force of gravity is slightly offset by air resistance. This results in a smaller magnitude of acceleration. Over time, this equates to less distance traveled. The comparison of these two plots is just what we expected. This concludes my lab presentation.